I'm starting probability theory, or probability. If you have any questions previously, just let me know. I can cover it. So we were talking about probability rules. Now, you can see what's happened that basically in first chapter, we're learning about parameters and inferential statistics, and then you're starting to learn how to organize the data into like histograms that will be used to do what we call the sample distribution to lead us to the true distribution, right? And now, after that, you got to where you're calculating these central tendencies, like the average, the sample deviation, p hat, all of these things that you're deriving. Now we're going to start assigning these things probability of occurring. So because we're going to do that, that's why we're covering probability theory right now. Probability theory is a class unto itself, but it requires calculus to have any understanding of it. And I encourage you all to go on to take calculus, because as far as I'm concerned, you haven't really lived until you take calculus, because without it, you can't see the matrix, you see. If you want to see the matrix, you need calculus and differential equations after that. So, oh, it's already got it for me. So, this with the symbol like that, like upside down, or like a camel hump. This is a probability of A and B occurring. These are events. An event can be a collection of observations that we pulled from the population, and this could be another set. How are those two sets related? If we have this idea of independence, okay, if this doesn't cause that, and the way to think about it is you're taking two cards from a deck. Is the first one affecting the second one? Well, if you replace it, right, the card that you drew, then the second draw is independent of the first, right? Yeah, okay, so that means you can write this then. If they're independent, you can write it like that, the multiplication rule. And if it's not independent, then we have this term right here. This means that what is the probability of B given that A has occurred and it's not being replaced? Okay, and then you multiply that times like this. This changes, right? Because this is with B given that A has affected it. Do you see? So it's a little more complicated, right? What is the analogy? The analogy of the one we just did previously was the probability of A or B, right? And that was equal to the probability of A plus the probability of B, right? Minus the probability in their intersection. And that's from up here. See the intersection? The probability of A and B. Okay? So, now, if this is mutually exclusive, that means you can draw a Venn diagram like this. And that's A, and this is, and this is B. That's A and B. In this case, you can actually look at it and see there's no intersection, right? If there's no intersection, then this term goes to 0. And that means it's mutually exclusive. Okay, mutually exclusive. That just means there's no intersection. All right, so the addition rule is this, just these two terms, if it's mutually exclusive. If they're dependent, you still add them up, but then you're going to have to come, if they're not mutually exclusive, that means there's an intersection, then you subtract, right? But then one would ask about this intersection, the same thing you would question here, whether they're dependent or independent. It's not the same as mutually exclusive, do you understand? Okay. So, so we'll do some problems with conditional. This is called a conditional probability. That's what that is. Okay, it's conditional because it's conditioned on something else, and we'll work some problems here shortly when I pull up the book. Is that okay? Any questions about this? We'll do some examples now, but basically, this thing here, this term, this with the line means given that A has affected B, is written like this: the probability of the intersection divided by, in this case, B affected A, right? So that should have been B, right? Because that's given that A is affected, so that's going to be A given B. Given that A's occurred, that goes down, yeah. So let's just suppose that we're not sure whether it's independent or not. If it is independent, you see this term here? If it is independent, then I can use this. I can rewrite this term. Do you see it? In terms of this. If we're not sure. Now, how could we test? Well, if this is equal to this, so we could say that this is the probability of A, right? And then this is the multiplication rule times the probability of B. Okay, that's how we can write over the probability of A. You see it? So that divides out. So if the probability of B given A is the same as just probability B, you know it's independent. Or even more so when we do it like this, when we look at an intersection, right? So we come to here. This is the probability of B given that A has affected B. Right? So here's the probability A. And here's the intersection. You see it? Right? And now, by chance, if they are independent, then I could write this back like this. See what I have here? Here. And my probability of A's come out, and it comes out to be, when it comes out to be this, when the product, the intersection is equal to the product, it's not, there's no, it's independent, not dependent. It means there's replacement. Then you can see it returns to this. This is what this is if it's independent. Correct? Because what's left when that strikes out, what am I back to? Probability of A times the probability of B, which is the definition for independent intersection. Does anybody understand the difference between mutually exclusive and dependence? Mutually exclusive means there's no common events shared in the observations, and independence has to do with the function of the experiment itself. The function of the experiment itself affects the intersection because that's the probability rule. The mutually exclusive or not is the summation rule of probabilities. Okay, good. Then let's go on to the text here. Let's try some of these and see how it works out. We'll get to conditional probabilities.
Sir?
Yeah? Oh, sorry.
Can you solve one before we get to the dependent?
You want to do one? Yeah, let's do one. Well, I'll do a problem in the book where it's dependent. Yeah, it's real not too bad. Let's say you're going to draw 2 cards from a common deck. So what's the probability of getting any one card? 1 out of 52, would you agree? But if you don't replace it and you're going to draw another card, that guy is going to come in at how many? Yeah, that's how you can do it. That means that it did affect. So this is dependent. If you replaced it, this one would be 1 over 52, right? This is an example of if you don't replacement. This is no replacement. So if there's no replacement like that, if you have a replacement, it's just like any other thing. Then it's going to be 52 times 1 over 52. Okay. This one had to be conditioned on the fact that this card was not returned. That's why that value changed. That's all it is. That's all it is. Just we have to modify this guy to take into account that we're not returning the card. When you had to modify it, that's talking about not independence, but a dependence. The second outcome is dependent on what happened on the first, because there was no replacement. Okay? But that's not the same as an intersection, right? When you have an intersection, that means you're sharing observations between two events. That's for mutually exclusive end and not mutually exclusive. Does that help? That works in problems, but basically this has to be adjusted on the second round, on the second draw. That's an example of a dependent. And how could I tell by looking? No, I had to look at the actual, how is the experiment ran? Is it ran with replacement or not? That's basically telling me whether it's conditioned or not on the first draw. We'll do some other examples. Okay. All right. Let's go back to the book. Let's talk about random variable. This particular term that I'm going to go over right now has been a confusion for students for years since we had it, because it's a little bit strange. You see where it says this is a type of distribution, right? We're talking about a distribution now. One is a bell curve that we've been using over and over, but they're not all bell-shaped. And they're not all continuous. So we have discrete, means it only happens at certain discrete. There's a whole course in discrete math. And then you have continuous. That means it's like if you're drawing, you don't lift your pencil off, it's continuous. So discrete random variables. First of all, I got to tell you what a random variable is. Just the random variable part. Okay, so random variable. Let me see if, okay, so we have this random variable. We know what a variable is, right? When you use a variable in algebra, you can always put a number into the variable, right? Like, yeah, I mean, if you have y equals 3 times x, you can pick values of x, right? And out come y. When x is 0, and y is 0, 3, and 1. And you can start to graph that. It has a slope of 3, so it'll be going up through the, okay, that's easy enough. But now when we have this other guy, here's the variable, right? And this is what we pick. So this is independent if you think of it that way, and this is the outcome. So this one is dependent if you think about it. It depends on what you put into x, right? X is the one that's leading the dance, and then that's the y. But if I'm talking about the probability of a random variable now, I'm going to put my random variables as capital X, right? And then if I want to say it's equal to something, an actual number, which I don't know either, I'm going to use the lowercase x. And that will be, say, a probability of, say, 0.95, for example. Just, we'll figure out what it is. But I want you to know that this variable is called the random variable. Okay, that's what this thing is called. But it's not truly random. That's what's so misleading about it. Why is it not truly random? Because we've done a histogram. We see that it's piling up in a certain shape. So this has a bunch of different shapes this random variable could fall into. But I don't want you to think it quite like this. Because this x's will be popping in and out depending on which experiment you run. It won't always be the same. But it's not truly random, okay? Truly random is white noise. There's no structure at all. You can't predict from it. Because it's just garbage in. You have no structure, you don't, or at least you can't find it, then it has no prediction ability, okay? So this random variable, unlike us picking, like here I picked a 0, a 1, and 2, right? These guys are going to be popping up with certain probability, and then you can do your y. We don't know what it's going to be till we actually run the experiment, and then it's going to be an actual little value. All right, so it'd be like something like this. Suppose we have a bell curve, and the bell curve's like this, and I have this little x here, right? See it? And I can ask, what is the probability that if I take a random variable from this kind of distribution, what is the probability that it's going to be less than or equal to little x? Okay? So because you built your histogram on your sample side, it gives you an idea what the population true distribution looks like, right? And then we can start making probability readings, estimates from this, because we can go like, okay, so for little x and all the way down, it will be the area under the curve from here on back. That is the answer. That's the probability, is the area under the curve back. It'd be like asking how many tallies fell in that cell, that cell, that cell, that cell, and then divide by n, you know, so you get your frequency, and then add them up from there on back. And that's what we use as our probability of being less than x, right? Or, if you seek, it might be easier to calculate this area. But we're going to answer this question if we want to, but, you know, this here, right here, you see it? So I could say that this is equal to 1, right? And then minus the probability that x is greater than little x. See? That's another way to do it, because the total area under the curve has to always be 1. 100%. There's, you know, when you do your tally, it's got to fall in one of the cells. Right? So it's 100% area under the curve, a probability of 1. I could take 1 and subtract this area to get this area. You get it? Why? Because this, I'm calculating from here over, right? I know that the area is 1. So if I take 1 minus that this is a random variable, capital random variable, is greater than x, 1 minus that will give me the probability that x is less than or equal to x. It sounds weird, huh? Less than or equal to little x. Right? You remember when we did it with events, that the probability of A not occurring is equal to 1 minus P occurring. Right? And any algebraic manipulation of that, you can see that if you bring this over, it's saying that the probability of A plus the probability of A naught is 1. Because in this case, what we're looking at is a Venn diagram like this. So this is A. So anything that's not in A is A naught. Clearly, if you take the probability of what's not in A plus what's in A, you better get 100%. Okay. All right, good. That's, yeah, we got to practice it. It's the only thing. Okay, now, here's what's required to be a true distribution. These are the rules. Okay, so they must satisfy 3 requirements, okay? Here is the sum. Remember that means sum? That's the sum of any discrete thing. It has to be equal to 1. That's the total area under the curve. And then, so if you take any subsection, well, anyway, what it's saying is probability itself cannot be negative. You can't have a negative probability. We don't know what it means. And of course, it can't be greater than 1. That's rule number 2. Because they'll ask you, is this a real probability distribution? And you have to check these things. Okay, and so there is a numerical random variable x. Remember, it's not truly random. That's what's misleading. Because when I was learning it, I go, well, if it's random variable, I don't get it. Well, why? There's no structure in it, because it doesn't mean that. And its number of values associated with corresponding. Okay. Here's a coin toss. Now, probability distribution of the number of heads. So this is like a histogram. Yeah. Yeah. It's going to, since it's where, you know, the fact that some phenomena is piling up in our histogram with a certain shape over and over, it gives us an indication what the true population must have a true distribution. So those probabilities pop up with a certain structure that would pile into a histogram a certain way. And that's not truly random because there's a structure in there. If the variable was giving observations off, if the true outcomes were truly random like they try to do in lottery, you couldn't use any past data to predict any future outcome. But if it keeps piling up in a certain way, we can take advantage of that. And so it is random in the sense that you don't know what the observation is going to, but it's not random in the fact that it's piling up with a certain structure. So here's the the sum of all the probabilities, right, of that. This is like a histogram. These would be like cells, right? But this is called a discrete distribution. Why? Let's show you why. Let me clear this out. Okay. One of the reasons is imagine this is these are like, okay, when you do discrete, there is no in between. It's either it's full integer values. All right. So when you throw the dice, if it's a fair dice, right, you don't have class width because it can only come in at 1, 2, 3, 4, 5, and 6, right? I mean that's 0. So the outcomes, I mean the way the face of a dice come out could be any one of these. All right? And because we assume that it's a fair dice, we would expect that your vertical here, right, and then you start throwing them, and you're counting, tallying them, and then if you divide by each one by n, you will get a probability of it happening. So this first guy will be 1. So you're going to have this as 1/6. That's the chances of getting a 1 out of 6, right? What makes it discrete is that we don't have anything like 1.5. It doesn't exist. So we call that a discrete distribution. Right? Because this one is, not only is it 1/6 across the board, because of this, that type of distribution is called a uniform distribution. Different than the bell. And it's discrete. Now, if some kind of outcome could take on any values between here and here, suppose there's some function that can take on any value from 1 to 6, then it would look like this. Then it would be solidly continuous. And continuous means that notice I'm not lifting my pen up to get to the next point. Only here I had to stop, start, stop, start, stop, start. This one is continuous uniform distribution. The other one was an example of a discrete uniform distribution. The bell curve is continuous. The reason we have that, even though this histogram was in blocks, right? We did this blocky stuff with a sample size of little n. But if we could manage to go out there and get the whole population in line, and we could actually do a histogram of the population, it'll look a lot more smooth because we have a lot more little observations to do, right? It gets to the point where, let's take something that's in electronics as analog. Analog would be shades of gray, let's say on a black and white. In essence, there's infinite shades of gray in there. It's not quite so easy because our eyes can't pick up certain differences in grades if they're too close to each other. So that's limiting. But in reality, you have infinite number of shades. So that's an analog process. That's a continuous process. Discrete would be exactly how the computer operates in zeros and ones. It's either 0 or 1. Unless we get to quantum computing, it's 0, 1, and then perhaps both 0 and 1 at the same time. Okay. Any questions on discrete and continuous? I know you've been exposed to this before in the earlier chapters of different distributions, but now we're going to get into using it to get our probabilities of event occurring from our random variable, which is not truly random. It's falling with a certain structure. Does any of this make sense, what I'm saying? Right. Okay, so the probability distribution of numbers of heads in 2 coin tosses. Now, you would expect, right, that this thing would be a 50% chance of getting heads or tails, right? But you're only tossing either this, or this, so the number of heads when 2s are tossed. No heads, 1 head, 2 heads. And that was the probability, but it's 2 coin tosses. So now what they did is that, look what happens. Is it a distribution of its own? Yeah, look what happens when we added them up. You got the 1. right? And you will, because you took your tallies and you divide by your sample size. That's how you got those. All right? And then, so this is a discrete random variable. Discrete because it's helping. There's no such thing as 0.5 in our experiment. There's no such thing as 1.5. It's in integer values. Just like the covalence of an electron going around the atom, it will go in different orbits, but only in integer jumps. When an electron gets hit by a photon, it picks up energy, jumps instantaneously. That's what they don't even mean. It jumps. It's like more spookiness at a distance, just poof, and it builds that, and then it starts orbiting on a higher orbit. So anyway, it's kind of unusual to find something in nature that actually happens only in integer values. It's really not too often. I mean, most things will have values that are in between integer values, right? But there's a function of nature that will only work with integer values, which is somewhat unusual in nature. Okay, any questions? Okay. Let's see. Okay. We will be learning about the binomial, and we'll be calculating the hell out of it. Because a binomial, it's an experiment that either only has two outcomes. Either you succeed or you fail. It depends what you're calling as a success. So if you had a kind of thing where you had babies, they're really going to be, let's say, a boy or girl. And whether a boy is born and a girl is born next should be independent, right? That whatever you had first, as far as I know, doesn't affect the next child you have. I don't know, and I'm assuming that's the case. So this binomial is used for that. And before we use it, we have to learn something called the counting rules. The counting rules is so that you determine the sample size. But let's say this is it. Let's say you have a briefcase, okay? And in the briefcase, has 4 tumblers on it, combination lock. You see it? And these tumblers are the ones, let's say it has 3 tumblers from 0 to 9, right? So I have to look at the probability of getting the right one. At first, what is your probability? Well, you have to find your sample size, little n, right? Now, it's not just about counting, but we have to use a counting rule to figure out how big the different samples could be. For example, you have this thing here, and, you know that the first one can happen 1 in 10 ways, right? I'm saying, yeah. 10, on the first tumbler of a briefcase lock. Okay? Now, here, 0 through 9 is 10. And since this one's not affected by this one, right, really, we have 10 again and 10 again. So you can see we have 1,000, we have 1 and then 3 zeros, right? And 1 out of that is your chances of getting it right with a guess. All right? Now, look at what happens here. Suppose I don't want to repeat any digit that I used earlier. Okay? So that means we're no replacement, right? So now look what happens to our sample size. This is 1,000, but in the other case, we're going to go 10, and this is going to be 9, and this is going to be 8. Why? Because we're not repeating. You see? So we need these counting rules that we'll go over. And we need one rule in particular before we're going to use the binomial distribution. I'm just getting you warmed up for that. Well, if I now have no replacement, I'm not reusing a digit, then this, you see, was affected by this. Right. If you restrict it, now, if you allow 2, 2, 3, and any combination, then it's 10 times 10 times 10. But if you're restricting the others two to not, right, then then you're restricting it because this one wasn't replaced, so it's 9 and 8 instead of 10 and 10. Does that make sense? I'm just saying, if you remember when you didn't return the card to the deck? It's sort of that, but we're imposing the fact that we don't want these to repeat any digit before, so your opportunity is 9 now. And after you thought second number, your next opportunity is going to be 8, because we're not reusing the same number again. Okay, so that we'll learn these counting rules, and then we'll get to that. Okay, back to the histogram. You know, when we had tallies, right, and you just had a graph with the counts of how many fell in each case, you know, those boxy things. And if we took that same thing and divided by the sample size, we got probability histogram, which we call a sample distribution. Do you remember? I guess you do. And then we have, so, okay, so you know, here it is. This was a discrete probability, right? So there was nothing between 0, 1, and 2. It's what we had earlier when we tossed. We had no heads, 1 heads, 2 heads. Okay, now it's not going to look like a fair coin because it depends how many times you run the experiment. So, but anyway, this is what you did before, your histogram, right? And before you would have a tally of how many fell in here, right? And instead of it here, this would be 1 and that would be 2, right? But if you take 1 and 2 and divide by sample size, now they change the probabilities. Same graph. Right, before you did just how many tallies were falling in there, that was a frequency graph. But when you had a relative frequency graph, that means you took the same scale, but you divided by sample size. Now, that's saying that what's the probability of getting a 0? Well, simply, it's from here on back. That's 25. What's the probability of getting a 0 or a 1? Now, then you're going to have this plus this, correct? You're going to have this probability plus that probability, right? And if you add them all up, it should be 100%, right? Because there's no other option. Everything has to fall in one of these sections. Do you see? You see now about the histogram? It's leading us to later on to be able to say, okay, we think the probability is this, and we'll go to that table to find the area under the curve to calculate the probability of something landing somewhere. You got a feel where it's creeping in? Okay. This is the hard part, I think, is to get it across to the next thing, because what we really want in this course is to forecast. And a hypothesis is a forecast. And now you're asking simply, does the evidence support my forecast or not? So you're using the evidence, the structure in the evidence, to help give you a probability of something occurring or not. That's a lot. Can you be wrong? Yeah, it's a probability. It's like the weather. You can be wrong, but you're going to be right with a certain probability. And how right you can be is interesting. And of course, you know, you can never be absolutely sure of anything. So instead of just go through your life making a guess, I'll go this way and this way. This is putting away that let the structure lead you in the direction that's probably most correct or more likely to be correct. Okay. Okay. So the probability formula in example 1 involves a table. So let's look at this here. It's a little bit of a leap. Have any of you know this symbol? I know you know that one. Are you familiar with this? This is like an excited eye. Mathematically. It doesn't mean that you have a very loud X or does anybody know this mathematically, what that means? Okay, so factorial means this. So you're going to have X times X minus 1 times X minus 2. Yeah, dot, dot, dot. So if you recall, remember on that tumbler, on that briefcase, if we decided that we didn't want the numbers repeated, correct? Then we had x. That was any way of 10 ways. This was one less than 10. And this is going to go all the way down till you hit 0. And you have to know, I might as well tell you now, 0 factorial. That means factorial. That means factorial. And that means the product. Also, 0 factorial is 1. You just have to believe it. Okay. Well, you should believe this, right? X to the 0 is 1. Same idea. I can prove it, but let's leave it at that. So if I ask you what the probability of 5, of the factorial of 5, it's going to be 5 times 4 times 3 times 2 times 1. And then this gets gigantic fast. You can actually find the limits of your calculator if you keep going with this, because you can imagine you're multiplying everything down. Oh, let's say I pick 100. Then you're going to have 100 times 99 times 98 times 97, all the way down. Okay? So this is the form of the formula. Consider this formula. So what that really is saying is, so any other value, of course, it's the same thing, right? So if I have 2, it's just 2 times 1. 1 factorial is going to be 1. Same as 0 factorial. But it won't work in 0 factorial, right? So let's say that I have this thing here. It's called, I'll just go ahead and do it. It's called a common, this is called a counting rule. Remember, we're trying to figure out how big our sample size is without actually counting every possible combination. So this one here, n, choose x. You may have never seen this either. Okay, so this means that we're going to take n factorial, okay, and we're going to divide by x factorial minus n minus x factorial. Okay, this is what you're going to do when you're going to have, when you're saying that you order matters. Order matters. Okay, and this one's called the permutation rule of n choose x. That is equal to this. That's going to be n factorial, just like this one, divided by, this was going to be n minus x factorial. The only difference is that we're not dividing by x factorial. You see it? Here we have everything. Let me rewrite it. You might not see it. It's n factorial over just this part. That's n minus x factorial. That's called the permutation rule, and this is the combination rule. They call it the permutation and let's see, combination rule. We'll go over that in a second. Let me show you how it works, because they're using it right here. As you can see, this x factorial, and then we have this 2 and 2 minus x. So anyway, when we're talking about this, remember our 3 tumblers, huh?
Can you explain the problem?
Yeah, it's the same one that we've just been going over, that one that, let me see. This one here, which came from the one before when we tossed some coins. That was right here. Okay, we were given an example of a discrete probability distribution. These are the requirements, as you remember, but here's the problem. Right here, they're telling you the probability distribution of the 2 coins. And this is the number of heads that they came up with tossing the coins. So we have that. This is when 2 coins are tossed, right? Oh. Okay, that's a good question. So, okay, now let's go to the next page. Go over here. Right here. Example 1 involves a table, but a probability distribution could also be of the form. It's another form. Consider the formula, this one, where x can be, this could be another kind of probability distribution. This is the equation here. So x can be 0, 1, or 2, right? Using the formula, we're going to find that p of 0. I'll show you how that works. But p of 0 means that you had no heads show up at all, right? So that means the random variable x took on a value of 0. So now you're going to calculate this with 0 in it, you see? And then we have a probability of 1. So you're going to have 1 factorial. For example, let's say if we try, well, any of them, but let's suppose we're going to try 1. So little x is 1. We know that x factorial, 1 factorial is 1, correct? And this is 1. So now I have 2. See the 2 here? This is they're trying to model they're trying to model it with this equation. And so they're saying that, look, watch, see if it works. So now we're going to go here. So what happens is, what I'm saying is that x factorial is equal to 0. I mean, equal to 1. Okay. All right, x factorial if it's 1. So I'm going to say that, well, I can't do that. 1 factorial is 1. Okay? And above that, 0 factorial is 1. And what's 2 factorial? Yep. And 3 factorial? 1 times 2 times 3. What would that be? 6? Right? That's 1 times 2, or the other way, if you want 3 times 2 times 1. Okay? And 4 factorial? Well, put 4 here, right? That would be 24. And 5 factorial, you see how it will start going up. So that would be what? About 96, something like that. You see what happens? Because I'm more, okay, so going back over to this, they're calling this a distribution probability distribution. Let's see if it works. They'll say, what happens if the random variable shoots out, shoots out a 0? So now the little x took on a value of 0, you see? So that would have been 1 times 2, and 2 minus 0 is 2. Do you see that? 2 minus 0 is 2, correct? And what is 0 factorial? 1. So this is 1/4, isn't it? So that does help explain this one, which had a probability of 0.25, remember? Yeah. See it? It worked. Let's see if it gives us this 50% when x is equal to 1. When x is equal to 1, so let's try now. Now it's a random variable, but this time we don't know what's going to pop up. This time 1 popped up. So we want the probability of getting just 1 head. So that's going to be little x now is equal to 1. And that's going to be equal to 1 over 2 times 2 minus 1 times 1 factorial. Does it work? Well, what's 1 factorial? That's right. So here we have 2 times 1, correct? So that's going to be 1/2, right? So it is an actual equation that tells you how it would fill up in that pattern. And of course, with 3, with 2 heads, we should get back down to 25. So let's try the probability of 2. It will now. Let's try 2. So here I have 1, right? And then I have 2, and then I have 2 minus 2, right? And then I have 2 factorial. So, I mean, it takes into account because here it just happened to be equal to 1. And the other one's happening, but now it's not 1 anymore. Right? Wait a minute. What happened there? Oh, okay, so that's 0. That's not going to work. It's in the denominator. How did that happen? Probably, he says a quarter. I don't see it right now. It worked for 1, but I don't see it with 2 because you got this. That gives you a 0 in the denominator, by the way. And you can take nothing and you can divide it by rocket ship. And when it goes through, you'll still end up with nothing. But we don't know what it means to take a rocket ship and try to divide it by 0 cases, 0 categories. It just doesn't make, right? If you had a 3, you would divide that by thirds. But we don't understand this. That's why I'm stopped, because that has a 0 in the denominator. Doesn't make sense to me. All right, we'll go on. I'll figure out what's going on in that problem. Maybe it's wrong. Well, that's never happened before, ever, in the history of mankind. It has happened. Yeah. I'll take a look at it and come back and see what this... because the 0 factorial is 1. But let me show you how it might take place. Let's look at this. Let's go back to that example of the briefcase. And let's see if we can apply those counting rules. Okay, so we had this one, and this one. Okay, now what we have, suppose that we're not going to have replacement, but we don't care which one you start with first. So whichever one you start with first, we'll start putting constraints on the other 2. So I'm saying that if you have, so if you have this, for example, you have how many n? Right, so you have n here, and then you're going to choose x amount. So we're going to permute, and that's just going to, that would be, okay, let me see if I can describe this. Suppose you have 3 positions, and this is president, vice president, and secretary. Okay? We say that order matters. Why? Because not every job interview is going to be president. Not everybody is going to be vice president. And so you have to select one, and then it stops the others. You can't, right? So now look at it this way. So now I got 3. Okay, and let's say order doesn't matter. So you have 3 janitor jobs to fill. It doesn't matter if the first guy fills that guy, or fills that guy, or fills that guy, because they're the same job. Understand? But over here, there are 3 different jobs. So it matters if you have a 1, 2, 3. That's different than having 3, 2, 1. These being the number, this like a job interview, and he's carrying a 1 around his neck, a 2 and a 3. Right? Where this, I can't count it anymore. Once I have 1, 2, 3, I've done counted that. Because it doesn't matter, any order of this still counts as 1. Does anybody know what I'm talking about? Okay. If I have 3 jobs to fill, okay, and I'm going to pick 3 of you. So I have to pick somebody to be president. That's a better salary than, let's say, vice president, and that's better salary than secretary. Okay? So if I pick you, and you, president, vice president, secretary, that's one possibility, but I could have picked him as president, vice president, and things. So I can either have you as president, or I could have the secretary as president. This is a different count. It matters because we have distinction. Well, I'm just trying to say, in what way can I fill those positions with 3 people? I could fill it at 1, 2, 3, or 3, 2, 1, or yeah, it'll be a problem that whatever the categories are, they're differentiated between whether I put you as president or whether I put you as. That's another combination that could happen. Is there another combination? 1, 2, 3. What else do I have? 2? 3, 1. You see? And 3, 1, 2. And what was the other one? Okay. Is there 1, 2, 3, 4, 5? Should be one more. Huh? 2, 1, 3. Okay. Now there are how many? There's 6. Which one? I got a 1 here, I got a 1 here, I got a 1 at the end. I got a 2 here, I got a 2 here, I got a 2 at the end. Do I have 2, 3, 1s? Okay, so then let's see. Well, let's make it 1, 2, and 3. Then you can run the 1 down, right? 2. There are going to be 6 of them, right? So let's see. This is back on. I don't know why it does that. Okay, but there are 6 of them, right? Let me show you. I don't know why that's not working. God damn it. Maybe I'm out of battery. Knock the probability up.
You have 5 of them right now, the 6th one that you're missing.
What?
You have 5 right now, the 6th one that we need is 1, 3, 2.
Okay. I guess the battery died. I don't know. Let me see. Is your brain cooking? Okay. So, yeah, you just run. You can do methodically. Run the 1 through. So 2, 1, 3, right? 2, 3, 1, right? And then we have to use the 2. So we don't have we can run the 2 on back. So we have 1, 1, 3, 2, correct? And then we need the 2 in the middle. We got it here, right? 1, 2, 3. So, and then so I need a 3, right? 3, 1, 2. Is that right? 1, 2, 3, 4, 5. And then 3, 2, 1. Okay, there are 3 people, but how many ways can I fill up the 3 different offices? There are 6 ways. I have how many ways? The question is, how many ways can 3 people be organized? Why 9? 3 times 3 times 3 would be 27, wouldn't it? But here, because they're combinations, I just have to pick all that. My sample size now is 6. Okay, there is no other combination. But look at this. Now, suppose I have 3 jobs that are of the same pay, of the same responsibility, right? How many ways can I put 3 people in there? No, 1 way. Because it doesn't matter. It's not an extra count, right? Because if I put this 2, 1, 3, it's still the same as 1, 2, 3, right? There's no change. Yeah. Well, what we have to do is, in order to find your discrete, remember we're doing discrete probabilities? In order to calculate, this is all about solving for the sample size. You know, before when we did problems, we had 5 observations, or we had 15 observations. You have a data, right? You had a table full of data, right? the total amount of observations that we pulled from the population, that total count is little n. Yeah? But sometimes, because of nature, we don't know what little n is, so we need these rules that kind of help us find out all possible combinations of the sample size. Now I know that in this problem, sample size is 6. Now I can start doing my frequency histograms by dividing those things by n.
Isn't that 1 and 2 stuff?
Yeah, it's all related, but how are you going to know the sample size? If you, yeah, but these counting rules are supposed to scare you. Okay, so now we want this, and believe me, it'll turn into probability. You'll see it in a second. Yeah, that's okay. If you have a question or homework, bring it to my attention. I'll answer it. If not, I presume that you're doing well in your homework. Who said we? Yeah. Yeah, that's good too. Well, and as far as I'm concerned, if you don't ask me it, I'm not answering. You got a question? Ask it. All right? I can't figure out what in your brain you're skipping. Do the homework, and if you have a problem with the homework, bring it to my attention. Okay? Have you asked me a question other than this type? Have you asked me a homework question? That's what I mean.
We have asked you a homework.
Don't start saying we. Speak for yourself.
Okay, I'm sorry. The lady that is not here today.
Don't speak for her. Speak for yourself. Right? I don't think you're a proxy vote for her.
This isn't like the case here.
It's a case, you're bringing it up. I'm saying, tell me what you feel, what you think. Ask me a question. What is it you don't understand? Okay, well then, if you're going to do everything, you better start with a particular problem from chapter 1. Okay? And we'll do it on the board. Other than that, I can't help you when you just say everything.
The homework on 3.2, question number 8, and solve it.
You know what it is?
I can run back to my dorm and grab my book.
All right, go ahead. Okay, in the meantime, we'll go ahead until he comes back with the problem, and then we'll solve it. Okay, so these are the counting rules. Now, like you said, this sort of thing might be set up so that, you know, we're going to run into the next problem, and it's going to have to do with, well, there we go. Why did it, oh, there we go. Okay, so let's just go on then. On the book now. I can't, this thing seemed to have died on me. Let's see. All right, now, here we go. Okay. Let's clear it out. All right, now let's go back over here. Now we can get back on track. Okay. This equation here, that's for what we call expected value, but I don't want to do that yet. Let's do the conditional thing that we were talking about earlier, so you can see a tie-in. Expected value. We're going to use this to figure out whether you should gamble or not and how much money you're losing. It's a decision theory. If you want to know what the chances of you winning or losing a game of chance, we use this equation. We take observation of x and multiply it by the probability of it happening. We do all of that. That's going to tell you at the end that if you keep playing this game, you're expected to lose 27 cents on every time you play. Like craps, like blackjack, right? And that's how it is. Okay, and now I want to do a conditional probability. Are we done? Is the class over yet? So are we in lab now, or still doing okay? Okay. So let me just get this adjusted because I'm looking for the conditional probability. Discrete and continuous we covered, and then binomial. This is the, if you recall the counting rule for combinations, that's the equation. Now, this one, remember, in this case, in the combination rule, order doesn't matter. So it would be the case of janitor, janitor, janitor. This is 4.3, or 4.4. Okay, that's the combination rule. Why? Because we have to know our sample size. And this one here, huh? What page? Okay. Okay, that equation? Okay, remember that we had on our question where I put janitor, janitor, janitor? Right? So this is the case where order doesn't matter. It's going to be smaller than this. And this is the permutation. I don't know if this is working now, is it? Okay. So now back to my trusty. Okay, so here's a permutation. I'm going to put this because order matters. But when order matters, it's a smaller set. Okay? And here's the permutation rule. N, choose P, and then choose R instead of little x. Okay? What's that equal to? It's exactly equal to this equation without the R factorial. So which one do you think is going to be bigger? Which rule is going to be bigger? N minus R factorial or the combination rule of N minus R factorial divided by R factorial? This one. Right? This is going to be a larger set than this one. Do you agree? Because we're not dividing by R factorial. Do you agree? Okay. So when order doesn't matter, right, you would expect the subset of these things to be smaller. So this is where order doesn't matter. Okay, order is not. And this is where it does. So when we had the janitor, 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 okay, well, which one is going to be the smallest set? Combination or permutation? This is going to be a smaller set, right, because we're dividing by R factorial, right? Yeah. So this, a 1, 2, 3 is the same as a 3, 2, 1, so we can't recount it. So this is going to be the smaller set. So this guy is going to be the combination rule, and now we have of this guy. So we're going to have, if you put it this way, you're going to have N is N3, choose 4, choose whatever one they want to choose. That would be R. So let's try it. So we have a combination of how many ways, well, so we have 3 candidates, right? And how many ways can they be organized? It'll be 6. So the N is what in this case? All right, so we have 6 factorial divided by 6 minus, how many do we want to look? However many you want to pick. Okay, so we got 3, and divided by 3 factorial, right? And what does this top guy mean? This guy. Yeah, but how do I write it? How do you write 6 factorial out? 6 times 5 times 4 times 3 times 2 times 1. And what's 6 minus 3? This is factorial. 6 minus 3. Yeah, 3. And what's 3 factorial? 3, 2, 1. Correct? And this is 3, 2, 1. Do you see it? That's 3 factorial. So that divides out, that divides out, that divides out. And look at this 2. Can divide into the 4, right? And there's 2. And then we could take this 3 and divide it in there 2, right? So we just have a 1 left below, right? So what do I have on top? 4 times 5 divided by 1. Because this 3 went into here twice. You see it? And that would be the combination. So here, oh no, they put n as 8. Because in our example it was 3, but it was 8 factorial. So you see I put in the 8. I put in the 8, and I want to know how many ways can you organize 3 people out of 8 people? Now we got 8 different people. How can I organize those 8 for 3 positions? First question, are the positions janitor, janitor, janitor? Or are they president, vice president, secretary? Yeah. Did you have a question? Okay. So In this case, it says how many ways can we order it? Does order matter? It does. Vice president, president, this. If it does, then look, 8 factorial is equal to, here, I'll do it here. What is it? 8 times 7 times 6 times 5 times 4. It's not a tech day. Okay, times 3 times 2 times 1. That's 8 factorial. And this one is out of 8 minus 3. I have 3 choices out of 8. How many, you know, it's going to be 56. You may have not noticed that, but if you line up 8 people and you got to put 3, and a 1, 2, 3 is different than a 3, 2, 1, right? Then we have a smaller set, right? So if you have a smaller set, so what do we got? What's 8 minus 3? And what's 5 factorial? 5, 4, 3, 2, 1. Well, that's handy, right? And what's this one? And what is that? 6. Okay, look at this. And there it is, 56. So there's 56 ways you can see how this is called the Salesman Problem. You'll see it a lot asked in college exams. Like you have 8 guys and you want to organize 4 of them. How many ways can you organize 4 people out of 10? How many ways can you organize 4 people out of 10, or 10 out of 4? Well, I'm saying, look at this permutation, okay? Which is the biggest set? This set or this set? Yeah. That is. Okay, so that means you have to count. In that case, a 1, 2, 3 is different than a 3, 2, 1. So this is a bigger set. If you're using this one, it's like all janitors, right? Because you're dividing. Huh? Okay, so let's say you have 10 guys, okay, and you want to fill 3 positions. Okay? So you got 10 guys, right? And you want to fill, you got 1, 2, 3. Well, let's just leave it at 5. You have 5 guys. How many ways can we put 3?
15.
Well, let's see. So what happens is that now you have to ask the question, does order matter or not? Does it matter? Well, I haven't told you what the positions are. If the positions are all for one, like electrician, right? There's no difference. We're hiring 3 electricians. You can't put Bob, and then you have Bill, and Bill, and you have some bat crazy thing. Okay? When you take the guy Bat and put him here, and Bob and Bill, it's the same. You understand what I'm saying? If this is janitor, you done fill the job. There's no more trying to fill combinations of this because they're all janitors or whatever. You understand? So, well, but the job itself has the same pay and it's the same position. There's no supervisor. Okay, thank you. Anyhow, you got it? So if this and Bat, Bob, and Bill is the same position, you're not going to count it. Right? Huh? Yeah, you're not going to count it because... So my question is, which one are you going to use it when order matters? The permutation. Why? Because a 1, 2, 3 or a Bob, Bill, Bat is not the same as this. It's another choice because these offices are different. Okay. Oh yeah, good idea. I'll take it next time. No, it's okay. I'll make sure everybody's here. I'll take it next time when things work better.